8.5, counting principles. What we should learn: how to solve simple counting problems, how to use fundamental counting principle to solve more complicated counting problems, use permutation to solve, and use combination to solve counting problems. So we're going to use permutation combination also. So these like last two lessons of this chapter are just about like introducing a probability and counting problems. So let's do one right here. 8 pieces of paper are numbered 1 through 8 and placed in a box. One piece of paper is drawn from the box, its number is written down. The piece of paper is returned to the box. So like you get that number, you put it back. Then the second piece of paper is drawn from the box and its number is written down. Finally, the two numbers are added together. How many different ways could 12 be obtained? So let's first think about what's going on here. We're going to draw from a hand of 1 through 8. So you can get 1, 2, 3, 4, 5, 6, 7, 8. We're going to put whatever piece we get back, and we're going to put it back. So we're going to draw again, and we have 1, 2, 3, 4, 5, 6, 7, 8 again. I want to know how many different ways could I get the number 12. Well, I get it from getting 6 and 6. That'll give me 12. I could do 2. I can do 2. I could do 4 and 8. That would also give me 12. Well, 8 and 4 would give me 12 also. And then how about 5 and 7? And 7 and 5. So it looks like there's 5 ways to get 12. I could do 6 and 6. I could do 7 and 5. I could do 5 and 7. And I could do 8 and 4 and 4 and 8. Right? We're only going between 1 and 8. So those are the only ways I could get 12 doing that. That's if we pick a number, put it back, and then pick a number again. So there's 5 ways to get 12. How about if we hope we do it again, but in this case, 8 pieces of paper are numbered from 1 to 8 and placed in a box. The two papers are drawn from the box at the same time. So in this case, when we list our numbers, 1 through 8, 1, 2, 3, 4, 5, 6, 7, 8. It's only from this pile here. So like, what was our list before? Our list was 6, 6, 7, 5, 5, 7, 8, 4, and 4, 8. Well, first things first. I can't get 6, 6, right? We're pulling at the same time, so it has to be any combination of two things here. So like 6 with something else, not going to get me 12, so that's gone. One strike through is fine. How about 7, 5? 7, 5? I could pull out a 7, 5, but honestly, in this case, 7, 5 is the same thing as pulling out a 5, 7. Because you only grab it at the same time, so it doesn't matter if you grab 5 or 7 with either hand from at the same time. So there's only one of those. And the same thing with 8, 4. 8, 4 gets me 12, but there's no difference between 8, 4 and 4, 8. Those are the exact same combination in this case. In this case, it is. So you don't need one of those. So there's only 2 ways. If you pull out these numbers at the same time, there's only 2 ways to get 12. You either get a 5 and a 7 in some combination, or you get 8 and a 4 in some combination. So it changes depending on if you pick one and put it back, and then pick again, or if you pick one at the same time. So let's talk about like a more concrete way of doing this. It's called the fundamental counting principle. So in our first 2 examples, we just listed all the possibilities, but sometimes that's not possible because there's just too many different ways. So we need a fundamental counting principle to help us out. And all the fundamental counting principle states is this: if the probability of A happening is let's say P, and the probability of B happening is, let's say, P2. And then what's the probability of A and B happening? Well, you just multiply them. P1 times P2. That's it. If I said that the probability of one thing happening is this, and probability of the other thing happening is this, what's the probability of that happening, then that happening? Just multiply them together. And it happens, and it could do with 3 things also. What's the probability of this, then this, and this happening? You just multiply all the probabilities. That's a fundamental counting principle. So let's do an example here. How many different pairs of letters can be from the English alphabet are possible? So this is a good example where we want to use the fundamental counting principle, because what they're saying is, right, A, that's a pair. How about A, B, A, C, and so on till you get to like ZZ. I don't want to write all those out and just count them all up. That's too many. So what we're gonna do is fundamental counting principle. How many ways could I get the first group in the pair? There's 26 letters in the alphabet, so 26 of them. And how many ways can I get the second in the pair? 26 of them again. So we're going to multiply those things out, and I get 676 possible pairs. So that's so much easier than like listing out all 676 and counting them up. So you see the fundamental counting principle. Another example. Telephone numbers in the United States currently have 10 digits. The first 3 are area code, and the next 7 are local telephone number. How many different telephone numbers are possible within each area code? Now, at this time, a local telephone number cannot begin with 0 or 1. Okay, so we have first 3 are the area code, and then we have the next 7 are your local numbers. Now, at this time, a local telephone number, so that's the local one, cannot begin with 0 or 1. So if we think about numbers, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, the 10 possibilities. Alright, so there's 10 possibilities here. Now keep on, we're only caring about the local numbers. How many different telephone numbers are possible within each area code? So we're only caring about this right here. Between each area code, how many different numbers do we have? So now the first number cannot start with 0 or 1. So out of these 10, we're going to skip to 0 or 1. So there's only 8 possibilities for that one. All the rest, everything's fair game. So we have 10, 10, 10, 10, 10. So we just have to multiply all of them together to find all the different possibilities. If we do that, we get 8 million. So within each area code, there's about 8 million different possibilities. So it's a lot. Permutations. So one of the key elements of fundamental counting principle, or important applications, I should say, is permutations. And that's how you order. Or arrange items. So when we do a permutation, we're arranging items in order. How we do that. So let's look at how many permutations of the following letters are possible. So how many ways can I rearrange these letters here? So there's 1, 2, 3, 4, 5, 6 letters. So in the first spot, I have 6 possibilities. I can do A, B, C, D, or E, or F. So 6 choices. In the second spot, well, I already selected one of the things. Let's say I selected A. Now there's only 5 possibilities. In the third one, I guess there's going to be 4 possibilities. In the fourth one, there'll be 3. In the fifth one, there'll be 2 possibilities. And in the sixth one, there'll be 1 possibility. So the way you rearrange things is just multiply down. So we're going to do 6 times 5 times 4 times 3 times 2 times 1, which is the same thing as 6 factorial, also known as 120. So that's what permutations are about. It's like how many different ways can you arrange things, and it turns out it's just a factorial. So the number of permutations of n elements is just n factorial. That's all it is. Okay, let's go to the next problem. Counting horse race finishes. 8 horses are running a race, and how many different ways can these horses come in first, second, or third? Assuming there's no ties. So we have 8 horses, and we want first, second, or third. So we don't want to arrange all 8 horses, just the first 3 is what we care about. Well, kind of the same idea. The first spot, I have 8 different choices, but once whoever wins, they're out of the pickings now, so there's only 7 left, and then there's only 6 left. So it's going to be 8 times 7 times 6, also known as 336. So it's 336 more ways that those 8 horses can come in first, second, or third. Now that's a special type of permutation, right? We're not doing all 8, we're only doing the first 3. That's like a subset, and there was a special form for that. So if we want to do a permutation of subset of NCR, we call NPR, we call this, right? Of the n different things, it's my bad R. Of the n different things we're talking about, I only care about the first R of them. So a permutation of n elements taken R at a time. So if you notice, it's just a factorial, but it's this form right here. So it's n factorial over n minus R factorial. So if we're going to do the exact same problem up here, just to give an example, I would be like, okay, we want to, out of the 8 horses, we want to pick the first 3. Now, you learn about permutation, order matters. That's the key thing about permutation. Order matters. Always think of the P as like position. So if the position matters, then you want to use permutation. So 8P3, so let's use this formula right there. So that's going to be, maybe that little negative sign looks bad. That's going to be 8 factorial over 8 minus 3 factorial. And we know how to do this. That's going to be 8 factorial over 5 factorial. Remember, the trick to doing this is you get the bigger number and you break it down till it matches the bottom number. So this is going to be 8 times 7 times 6 times 5 factorial. And I'll stop there because that 5 factorial can cancel with this 5 factorial. And you get 8 times 7 times 6, also known as 336. It's like we did. So that's permutation, right? So if you're picking a smaller set out of a bigger set and order matters, we're going to do a permutation. That's the form we're going to use. Now, combination is the same concept, but in this case, order does not matter. So it does not matter which you get first. So if you have a sequence of A, B, C, it's the same thing as getting B, A, C. Think about if you play cards, like poker, and you get a hand of, you get ace, and then they give you a queen, and then an ace, and then like a 2 and a 3. That's the exact same hand if you got 2 first, and then 3, and then an ace, and then a queen, and then an ace. They're the exact same hand. They're all in your hand. It doesn't matter which order you got them in. You still have your hand. Where anytime you run a race, order matters, right? 876 is very different than, or I should say, ABC is very different than CBA. So like a password or a race, order matters. That's a permutation. When it's just a collection of things, that's a combination. When order does not matter, combination. And we have a special form for the combination. It's like a fancier one of the permutation. It's a permutation, but then we also divide it by R again. So again, you'll have these formulas, you gotta use them. So let's do an example. In how many different ways can 3 letters be chosen from the letters A, B, C, D, and E? See, in this case, order of 3 letters is not important. It doesn't matter. I just want to care about what 3 letters you get. It doesn't matter what order they come into. So there's 1, 2, 3, 4, 5. So it's going to be 5 total. And I only care about 3 of them. So we're going to do the formula, which is 5 factorial over 5 minus 3 factorial times 3 factorial. And this is, I put the parentheses in the wrong spot there. There we go. Okay, so on the bottom here, this is 2 factorial, 5 minus 3. So I'm going to keep the bottom 2 factorial times 3 factorial. On top, we're going to break this down. Remember, you only want to break it down until you get the highest one, then you're going to stop. So 5 times 4 times 3 factorial. These cancel out. We get 5 times 4 over 2 factorial, but 2 factorial is 2 times 1. So you can reduce after, you can reduce before. I'm going to reduce right now. So I get 5 times 2, which is 10. So 10 different ways to rearrange these letters and to pick 3 of them out. A standard poker hand consists of 5 cards dealt out of 52. How many different poker hands are possible? As the cards are dealt, players may reorder them if you want. So if you ever play poker, when you get your 5 cards, it doesn't matter which order you get them. As long as you get them, you get them. So this is going to be 52 C5. So using the formula, it's 52 factorial over 52 minus 5 factorial times 5 factorial. So this is 47 factorial. So on top here, we're going to have 52 times 51 times 50 times 49 times 48 times 47 factorial. That's where I'll stop there. On bottom, we have 47 factorial. Then we have 5 factorial. We'll write it out. It's 5 times 3, 4 times 3 times 2 times 1. This and this cancel. We probably need a calculator for this one, otherwise it'd be way too big. And the answer we get is 2,598,960. So a lot of poker hands there. And that's the lesson.